Good morning and welcome to Computer Science 331. It's not 331, it's Computer Science 311. It's a good thing to know which class you teach. For our final topic, we're going to be talking about balanced trees. Specifically, we're going to be talking about balanced binary search trees. And I guess I want to discuss what is the problem. And the problem has to do with how entries might come into a binary search tree. For example, suppose we wanted to insert, we'll make this really bad, 1, 2, 3, 4, and 5. Well, if we did that, we would have a binary search tree that would look like this. We would have 1 over here, and then there would be 2, and then there'd be 3, 4, 5. Likewise, if we started with a different tree, where it was 5, 4, 3, 2, 1, again, then we're going to get something that looks like this. And in a perfect world, we would get something like this. We would get 3, and then we would get 2 and 4, and then maybe we'd get 1 and 5. What's that going to look like? Well, we'd come in here and we'd get 3, and then over here we would get a 2, and over here we would get a 4. Actually, that wasn't the best situation, was it? Then I'd get a 1 and a 5. That's not too bad. Okay? The idea here is that if you're not careful in a binary search tree, remember the ideal binary search tree, ideal search time, we would have that big O of n is equal to log n. In other words, if the tree were perfectly balanced, like this, okay, search time would be log n. On the other hand, when it degenerates like this, we're going to get the big O of n is just equal to n. And there's a big difference between log n and n. So the idea here about balanced binary search trees is can we come up with a data structure that has all the properties of a binary search tree, meaning that for any node, we have at most 2 nodes coming out of it. Anything to the left is less than it. Anything to the right is greater than it. And it can maintain some sort of notion of being balanced. And what we're going to be doing in this section here, first of all, we're going to be talking about these things called red-black trees. And these are not a perfect solution in the sense that these are not going to guarantee us that we're going to get log n performance. But they give us very good performance, which means that it's never going to degrade into this over here. So today's topic are these things called red-black trees. You will note that I have given you a handout. There is a section in the book on red-black trees, but my colleague, who is now retired, Susan Haynes, I think has actually put together a very nice document right here that is going to explain the mechanics of a red-black tree. And I think what we're going to do is we're just going to follow this along. Now, there is some notation that we have to get used to here. So what I'm going to do is I'm going to pull this away, and I'm going to come over here. Just give me one moment. Okay, so some notation. Okay, a couple of things here. We want to talk about some node x. So we're going to have x and that's going to be a node. And we are going to have P, and that's going to be the parent node of X. And then we'll have G, which is the parent node of P, which is another way of saying it's the grandparent of X. And there are a couple of things we want to note here. There are several relationships that we could have here. I could have something like this, where there is G, and then I come over here, and here's P, and here's X. And I could also come over here, and I could have G, and here's P, and here's X. And in this sense over here, I want to say that X is an outside grandchild of G. And then the other situation I'm going to have is this. I could go G and come over here to P and then X, or I could have G coming over here to P, and this could be X. And here we would say that X is an inside grandchild of G. Okay, so keep these definitions in mind. We're going to be referring to these a lot. And I want to go back to Dr. Haynes's right up over here. And so you can see here are these cases that I just explained to you. So anyway, this is very important right over here, the red-black tree rules. So first of all, it says that every node in the tree is either red or black. And it says over here, any node except the root can change color as demanded by balancing operations. A little bit of history here. Originally, when this idea was proposed, and it was back, I think, in the early 1970s, there wasn't the notion of a red-black tree. It was just that the node had a bit. And in some of the nodes, the bit was set. In some of the other nodes, the bit wasn't set. And basically, being set corresponded to it being red. If it wasn't set, it was called black. So the question was why was it called a red-black tree? And the answer is, back then, the printers that they had only had red ink in them, and they only had black ink in them. So thus the name red-black was born. But if you prefer blue and green, you can call them that. You can give them any old name that you like. But we will stick with red-black. And we will follow this along. So every node is either red or black, okay? The root node is always black. And we're going to see that the colors of these things can change, okay? So here's number 2, the root is black. And we come to rule number 3, and it says if a node is red, its children must be black. And please note the converse is not true. A black node can have black children. That's not a problem. And here's the key point right over here. We say that every path from the root to the leaf must contain the same number of black nodes. Now that is an important property, and I want to explain now where that gets us or why that is advantageous. Okay, so remember, we talk about, we said that every path from root to leaf node contains the same number of black nodes. And if you like, we'll refer to this, we'll call this the black height. So what we're saying here is that, first of all, we are not guaranteeing that this tree is necessarily going to be balanced. But we can say something like the following. If we have something like this, and this is black, and this is black, and this is black, and this is a leaf node. So we have a black height here of 3. Then what we can have over here, and here you're going to have to excuse me because I'm going to have to play around with colors, and that's going to take me a little time. That the very worst case we could have over here is that now that should be showing up as red, and it isn't. I'm going to call that red. We'll do it this way. Black, red, black, red. Okay, so this would be 1, 2, 3, 1, 2, 3. And notice the length here is 3. The length here is 6. So basically, what the red-black rule is enforcing us to do is it's saying that basically the longest path is at most twice the length of the shortest path. So the point to realize here is that red-black trees aren't necessarily balanced, but they don't get very much out of balance. This is the absolute worst case that you could have, would be a situation like this. Okay, let's just review that a little bit more in detail. You'll notice over here when I was drawing this, I went black, red, black, red, black, red. And you may be wondering, why aren't there any cases where there are 2 reds in a row? And again, I am going to say, well, if in constructing these trees we have adhered to the rules, and I want to point out to you rule number 3 down here, if a node is red, its children must be black. So we can never have the case that there would be 2 reds in a row. So at the very longest, we can have these guys alternating like this. And again, this would be at most twice as long as that one over there. That's the whole desirable property of these things. So now let's talk a little bit about how we maintain these things, or how do we insert things in these trees. And for this exercise, we are only going to be talking about insertions. We're not even going to consider deletions here. But there are a whole lot of things that we need to keep track of here as we're going to go ahead and do this. So here are, look at that, there are 3 rules here that we have to keep in mind, and they're fairly complicated rules about how we're going to insert new nodes. So the first thing you have to know is that whenever you insert a new node, with the exception of the root node, which is black, all new nodes are always going to be red. So that's the first thing that you have to keep in mind. So it says right over here, and this is a very key point, when inserting a new node, there are 3 processes that are followed in the order given here. So the first thing is as we're making our way down, remember this is a binary search tree, so that all new nodes are going to be inserted down as leaf nodes. So we have to travel down the tree to get to the point where we're going to eventually insert. But the first thing that we will notice is it's possible that we may do color flips on the way down. And basically the rule is that if I encounter a black node with 2 red children, I'm going to flip the colors, okay? What's going to happen is I'll make the black node red and I'll make the 2 red children black. The only exception to this is when I'm looking at the root node, okay? If the root node is black and the root node has 2 red children, then what I'll do on the way down is I would make both of the children black, but I would leave the root node as black. So it says over here that if you go ahead and you make these color flips, what's going to happen is you may have violated the red-red rule, okay? And what the red-red rule means is that you now have a node that is red and its parent is red, and that's a violation. So what we have to do here is if after making these color changes, we have to go into these complicated rules here with rotations. And I want to explain how the rotations work. Okay, so the rotations look something like the following. And we can have one of 4 situations, but they actually reduce to being 2 situations. So one situation you have is that we have a node here like this, and this is a grandparent, and then we come over here, and I don't know why I'm not getting the colors here. Give me a moment here, folks. I should be getting colors, and I'm not getting colors. I don't know why. Now I think I'll get them. Yeah, there we go. Let me just... Now we have a big mess. Please bear with me, folks. I promise this will clean up in 1 second. Well, that really looks bad. Okay, so I want to assume that I have a grandparent G, and then I have over here, I have a parent, and then over here I have a child. And somehow I can't get the colors to work, but this would be black, this one would be red, and this one would be red. And what I am going to do here is I'm going to do a rotation. And what's going to happen is I'm going to promote the parent. The parent's going to come up to here. The grandparent is going to come over to here. And the child is going to come over to here. And what happens is I'm going to turn this red. This one already is red. And this one would be black. Okay? And I think you can see that the other way that this would go would be exactly the other way. If I had a grandparent here, and then a parent here, and then X over here, and this was black, and this was red, and this was red. Again, what I'm going to do is I'm going to change this so that, and again, we can imagine there's something pointing over here. I'm going to have the parent over here. That's the parent. And what's going to happen over here is over here is the grandparent, and over here is the child, and this is going to become red, or this stays red, this becomes red, and this one over here is black. So these are what are called rotations. We're rotating, in this case, we're rotating this way. In this case, over here, you can see what's going on is we are rotating back that way. So I hope that's clear to everyone. Now the other cases here, they look more complicated, but they really aren't. And I have the situation where there's a grandparent here, and then over here, there's a parent, and then over here, there's a child. And again, we're in the situation where this is black, and this is red, and this is red. And the first thing we do is we're going to flip these guys around. We're going to go up there, and we're going to bring these guys down here. And I get the following. I get a grandparent that is black. And now what happens is I come over here, and I've got X, which is red. And now I come over here, and I have a parent, which is red. And now notice this situation over here looks just like this situation over here. So I go ahead and I do my rotation now. And now what's going to happen is X comes up here. Okay. And G comes over here. And P comes over here. Okay, and what happens over here is X becomes black, and the grandparent becomes red, and the parent already was red. Everybody get it? So this, what we do over here is we first do this transformation here. And now this becomes this situation over here. And you can see the same thing is going to happen over here. If I've got a grandparent that's black, and I come over here, and I have a parent that is red, and then I come over here and I have the child that is red, the first thing I do is I'm going to flip these two. So I get the grandparent, which is black, and I come over here and I get X, which is red, and I come over here and I get the parent, which is red. And now you'll note that I'm in this situation over here. And what I'm going to do is I'm going to come up here and I'm going to, X is now going to become black. And I'm going to come over here and the grandparent is red. And I come over here and the parent is red. So these are the 4 different possible transformations we can do on the way down. Now remember what happens when we do this. We do this if when going down, we first have to do a color change. And the color change occurs when there is a black, when you encounter a black node with 2 reds. When I'm in this situation over here, okay, then I'm going to go ahead and switch these and I'm going to get a red, black, black. But it may be the case that there was, that this one's parent was also a red. So that when I now have this red violation, I am going to do one of these over here to fix that up. Okay, and we'll see examples of this shortly. Let me save this. Close it up. Now the other thing that we have to do here, so remember we said there are 3 different processes that we have to do here. On the way down, we can do color flips. If when we do color flips, we get a red violation, then we have to do this recoloring and this rotation. Finally, when we get down to do the actual insertion down at the leaf, remember we're inserting a red node. New nodes are always red. So if the parent is black, you're done. There's no problem at all. But it could be the case that the parent of where you're inserting the new node is red. And what will happen here is if you look at these 2 rules right over here, they're basically just a restatement of the rules that we had right up here. Okay? So what we're going to do now is we're going to work through an example. And we're going to start off with an empty red-black tree. And here are the numbers that we want to insert in order. So the first thing we're doing is we're inserting 60. It is the root node. The root node is always black. Okay, we're going to insert a 20. Remember, new nodes are always red, okay, except for the root node. So I come over here, I look at 60, I insert a 20, it goes down there, it's a red. I insert a 75, I come over here to the right. And notice here that I now have a black with 2 reds, but I'm not going to do anything about that until I go ahead to the next insertion. So on the next insertion, it says to insert 10. And now what happens is notice I have a black with 2 reds. Now the rule says to make the black red and the red blacks, except in the situation when I'm dealing with the root node, which is what I have right over here. So what I do here is I do have to make the 2 children black nodes. And then I go ahead and I just insert the 10. And we can see that the 10 is going to go off to the left. And here is the result of inserting the 10. Okay. I come over here and I'm going to insert the 85. I come over here, I have a black with 2 blacks, there's no violation there. I come over to the right because 85 will take me to the right. Okay, and at this point, I'm getting ready to insert. I don't have to do anything funny because I'm inserting a red node that has a black parent. There is no violation. Now some fun begins. I'm asked to insert 100. And again, as I make my way down, there is no violation at all. But now when I come over here and insert the red 100, there is a violation. Okay, I've got a red here. So if you remember what the rule is now, what I've got to do is I'm going to rotate this up. The 75 is going to come down. the 85 will become black, and the two children are both red. And that's exactly what's happened over here. So now we have to insert an 80. And what I want you to do is I actually want you to look up at this drawing here. Because what's happening now is as I come to the 60, there's no violation here. I come over here and I have a black and two reds. Well, my rule says on the way down, if I have a situation like that, make this red and make both of these black. So you can see that's exactly what I've done over here. Okay, and we can see that the 80 is just going to come right over here and it's going to be red. And that's exactly what I see in this drawing right over here. So far so good, but some complications will be coming up shortly. We are asked to insert a 35. There's no color violation here. There's no color violation here. Okay, I'm going to go to the right and I insert my 35 and I'm all done. Now we can see I've got a black and two reds. The next time I come down this path, I am going to be changing those, but it's not changed now. It's only when I'm going down the tree. So now I'm asked to insert a 5. And we can see I'm going to come down here, and you can see already what we've done is we have inverted the colors. Okay, I got over to the 20, the black 20 with the two red children, and I inverted the colors. So I now have a red 20, two black children, and now I can come down and I can insert the 5, which is exactly what I've done right over here. By the way, there are a couple of things to notice. Notice that if I go from 5 up to 60, I have two blacks. If I start over here at 35 and I go up to 60, I've got two blacks. If I start at 80 and I go up to 60, I've got two blacks. And if I go from 100 up to 60, I've got two blacks. I've maintained the black height, okay, for any path from a leaf node up to the root node here. So we are going to insert 18. So 18 is going to take me to the left here, okay, and I don't see a problem here. And I'm going to come down here, and I don't see a problem here, and it looks like I'm just going to come right over here, and there's going to be an 18 inserted right off of the 10. And that's exactly what I have. Okay. So I'm going to come over here, and now I'm asked to insert a 2. And when I am asked to insert the 2, I am going to come down to here, no violation. There's no violation. Here's a red with two blacks. There does not appear to be a violation here, so I would insert a red 2 just off of the black 5. And that's exactly what I've done. Now I'm asked to insert a 4. There's no violation. There's no violation. Over here, there's no violation. I come over here. I'm still going to go to the left. And now I'm going to come down here. So there's going to be a 4. There's going to be a violation because I'm going to have a red violation. You can see it's right there. And let's think about what the rules tell us to do. The rules tell us to do in this situation here that what I'm going to do, remember, this is an inside grandchild here. I'm going to rotate the 4 over to here, and the 2 is going to come down to there, and then I'm going to promote the 4 up to here, and the 2 will go to the left, and the 4 will go to, and the 5 will go to the right. Right over there. Okay? We saw that we changed the colors as the prescription told us to change the colors. And again, I want you to notice as I start at 2 and I go up the tree, now I have a black height of 3. If I start over here and go up the tree, a black height of 3. From here, a black height of 3. From here, it's a black height of 3. Any one of these, I've maintained it all the way down. Very, very cool. Okay, so starting with this tree now, we are asked to insert a 3. So let's take a look at what's going on up here. I have the 60 and there's no violations. I come down here to the 20 and there are no violations. I come down here to the 10 and there are no violations. I come down here to the 4 and notice I have a black 4 and I have 2 red children. So the rules tell me that what I have to do is I have to make both of these children black and make that one red. So that gets me over to here. But now notice I have a red violation. There's a 10 and a 4. And notice that this is an outside violation here. Now you have to watch this one closely because this one is a little bit tricky. I'm still going to do the same thing as before. I'm going to move the 10 up, okay, and the 10 is going to become a black. What is going to happen is the 4 will come off the left of the 10, but now the 20, and actually the whole subtree to the right of 20 has to move to the right of 10. And that's exactly what has happened over here, okay? You can see that the 10 got promoted up. Everything that was over here, the 20 and the 35, that came down over here. And look at what happened to the 18. The 18 jumped, okay? It jumped from coming off of the 10 to coming off of the 20. So we actually had a subtree that had to move here, all right? You can see that we've recolored these things now. The 10 has now become black, and we can see that the 20 has now become red. Okay, now at this point, remember the goal here was we were trying to insert a 3, and we came down here, and here our 3 got inserted. Again, I want to point out to you that if you consider the black height of this tree going on up from any one of the leaf nodes, it's going to be the same. Okay, that is the end of the example. It's probably this last step here that you should study the most closely. It's the most complicated one because you actually had a whole subtree that was moving over.